Welcome to Get Your FRQ On. This question is from 2016. It's question 4, and it is not calculator active. In the question stem, we have a differential equation of the form dy dx equals an expression, and that's it. In part A of this question, we are asked to sketch the slope field for the 6 points provided on the graph. So the first thing you're going to want to do here is actually use the formula for dy dx at the 6 ordered pairs and calculate what the slope would be at each of those points. So at 0, 0, it's 0. At 0, 2, it's negative 4. At 0, 1, it's negative 1. At 2, 1, it's positive 1. At 2, 0, it's 0. And at 2, 2, it's 4. All right, so using that information, we're just going to graph little segments whose slopes are equal to what we found. Now, in order to get the points for this, your horizontal segments need to be horizontal. Your segments whose slope needs to be 1 or negative 1 needs to be pretty close to 1 or negative 1. And then after that, like this one over here is 4, this one is negative 4. Notice it's just considerably more steep than the one beneath it, which should be either 1 or positive or 1 or negative 1. So it just has to be reasonable. Notice that the expression for dy dx is not defined when x is equal to 1, so don't put anything where x is equal to 1. Don't put vertical segments there. Don't do that. The slope is undefined, so you would not mark anything when x is equal to 1. All right, part B of the question, if f of x is a particular solution and f of 2 is equal to 3, write the equation of the tangent line to f of x at the point 2, 3 and use it to approximate f of 2.1. All right, so using the expression for dy dx to calculate the slope of the tangent line at 2, 3, we're just going to plug in 2 for x and 3 for y, and we get a slope equal to 9. All right, using the fact that this needs to go through the point 2, 3, we can write the equation for the tangent line in point-slope form. We can convert it into slope-intercept form, which for this problem might help because we are going to use that to approximate f of 2.1 later. But at least in point-slope form, it's going to be y minus 3 equals 9 times x minus 2, which becomes y equals 9x minus 15. And then if I'm going to use that to approximate f of 2.1, I'm just going to plug in f of 2.1 for y and 2.1 in for x and simplify that. 9 times 2.1 is 18.9. 18.9 minus 15 is 3.9, so f of 2.1 would be approximately 3.9. And in part C of this question, we are asked to find the particular solution f of x given the initial condition that f of 2 has to equal 3. So we're going to use separation of variables here because for problems like this, we really don't have any other methods in AB. In fact, oftentimes if you see a question like this in a free response question on an AB exam, you have to use separation of variables because it's really the only way you know how. It's an AB test, so they're only interested in AB methods. So if I have dy dx equals y squared over x minus 1, dividing by y squared, multiplying by dx, and then taking the antiderivative of each side, all right, and then actually taking the antiderivative of each side, we get negative 1 over y equals the natural log of the absolute value of x minus 1 plus the constant. Then we're going to use the initial condition f of 2 equals 3 to solve for a specific value of c. So I'm just going to replace x with 2 and y with 3, so I get negative 1/3 equals the natural log of absolute value of 2 minus 1 plus c. 2 minus 1 is 1, natural log of 1 is 0. So we get that c is just negative 1/3. And now I can set the c equal to negative 1/3 in my sort of general solution. So I get negative 1 over y equals natural log of absolute value of x minus 1 minus 1/3. Don't get too fancy here. I'm just going to swap the numerator and denominator, and I'm going to get y equals negative 1 over natural log of absolute value of x minus 1 minus 1/3.